Hey guys, welcome back. In this part, I'm going to talk about tubes that are open at one end. And when we have constructive interference and we have standing waves and resonance in this case, which is going to be a little bit different than strings fixed at two ends or tubes open at both ends. So if you remember, tubes that were open at both ends and strings that were fixed at both ends. For the first one, we had a half of a wavelength was equal to the length for the first harmonic. For the second harmonic, the wavelength was equal to a length. For a third harmonic, the wavelength was equal to 2/3 the length. So you can get 1.5 wavelengths in the whole length. This is going to be a little bit different. So if you have a tube that is open at one end, it's only going to be constructive interference if you have a quarter of a wavelength in there, and that's your first harmonic. And then there is no second harmonic. There's a third harmonic when you have 3/4 of a wavelength inside here. And then there's a fifth harmonic when you have a 1.25 wavelength. So it's only going to have odd number harmonics. And I'll demonstrate some of these for you guys in class as well when we get to them. A good example of this are organ pipes. And so again, I like to think of the picture and not so much the equation they put in your book or in the notes. So I like to be able to visualize it, that it has to have a quarter of a wavelength, and then it has to have 3/4 of a wavelength, then 5/4 of a wavelength. And this is only going to be if it's open at one end. All right, so find the first 3 harmonics for an open at one end tube that is 0.23 meters long. So our tube isn't changing. Our tube is going to be the same, and we're saying that we can fit a quarter in the first one. So that's going to be a quarter wavelength in and a quarter wavelength out. Realize that I know that sound is a longitudinal wave, and I am drawing this wavelength as a transverse wave. Then I'm going to have 3/4 in and 3/4 out. And the idea is that you don't want destructive interference. So when we have this, we have our antinodes matching up, and we have our nodes matching up. And we have, when we get to the end, that bounce back that we see. And then for the next one, it's going to be 5/4. And again, I like the picture. I like, for me, visually, especially with the strings, if you think about the demonstration I did with you guys. All right, so what is constant for these is going to be our speed of sound. We're going to use 343 again. They would have to give that to you because it varies. And so I know that for my first one, my length is a quarter of a wavelength. So 4 times my length is going to be a wavelength. So V is equal to F lambda. F1 is going to be V over lambda. So this is going to be 343 divided by 4 times 0.23. And so I have almost 373 hertz. So that's our fundamental frequency for this tube open at one end. For the second one, I have 3/4 of a wavelength in the length. So that tells me that 4/3 of L is going to be my wavelength. This is number 1. This is number 3. And this is number 5. So F3 is going to be V over the wavelength. Again, the velocity is constant. It's the speed of sound in air. And I'm going to divide this by my wavelength, which we said was 4/3 L. So I'm going to get 343 divided by 4/3 of 0.23. So I got 1,118. Okay, so for the fifth harmonic, because we only have odd harmonics for tubes that are open at one end, I know that I have 1 1/4 wavelengths in the length. And so I have 5/4 wavelengths in the length of the tube. And so I know my wavelength is going to be 4/5 of the length. And so I'm going to plug this in. And I got, whoa, what was that? 1864. Is there another way to do this? Is there an easier way to do this? Yes. And it goes into why this isn't the second harmonic and this isn't the third harmonic. Because you remember when I did it in class for you guys with the standing wave with the spring, to go from the first harmonic to the second harmonic, I doubled the frequency, how often I put my hand up and down. And that's why this is the third harmonic, because it is 3 times our original frequency. And so I could say that the next harmonic, the third harmonic, is going to be 3 times our fundamental frequency. And so that's going to be 3 times 373 hertz. And if I count for rounding, I should get the same thing. And I got 1,119, where I got 1,118 there. For my next harmonic, which would be the fifth harmonic, because the frequency is 5 times, not because it's the fifth in an order of 5, that's going to be equal to 5 times the fundamental frequency. And I'll demonstrate these harmonics for you guys in class, or I already have. And so this should be 5 times 373. And I got 1865. And so you can see that it's showing us our overtones for different instruments. And this accounts for why different instruments sound different playing different notes. And you can see that for different instruments, you're going to have, some of them have a lot more overtones, and some have barely any of the overtones. Some have kind of in the middle, looking at the clarinet or piano or violin. And this is an example of sound waves interfering. I'll do this demonstration as well for you in class with the phenomenon of beats. The idea is if things are very close in frequency, that you'll hear like a wah, 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 wah. And how many wahs you hear per second is how many hertz different that the things are. And it'll be easier to see once I do the demonstration for you guys. So, and that will be constructive and destructive interference happening over and over again. And so if you have something that's just off by, 1 hertz, you'll hear just a wah in 1 second. And then if you're off by 3 hertz, you'll hear a wah, wah, wah in 3 seconds. So if you want to know how many beats you have, say we have something that is 68 hertz, and then a second tuning fork that is 65 hertz. It is a 3 hertz difference, so that is going to mean that you're going to hear 3 beats per second. So this accounts for 3 interference patterns, right? It's going to interfere 3 times every second. So what is this going to look like? And again, we're assuming that we're drawing a transverse wave to show something that's actually a longitudinal wave, which is frustrating to me. But you can see that they start off close together and then they're spreading apart. At some point, they're going to perfectly cancel out. And then as they cancel out, they're going to come back together. Then they're going to get back together and get bigger. And that's the wah we hear. And then this is going to happen again. This is 60 hertz and 50 hertz. So that's a 10 hertz difference. And so that means you're going to get 10 beats per second. And so it tells us that the beat period is 0.1 because of constructive and destructive interference. The diagram on the right shows a wave in a particular moment in time as it travels along a rope in the direction shown. Which of the following statements is true about point P on the rope? Since the velocity is going this way, that means that at a time a little bit later, this wave is going to be shifted that way. So that means if P was here, now P is there. And it tells me that it's moving upwards, up. The rope itself doesn't move down, just the pulse does, right? A standing wave is generated on a string which is fixed at both ends and vibrates at a fundamental frequency. The tension in the string is now increased, and now a new standing wave is vibrating at its fundamental frequency is generated. Which of the following statements about the properties of the wave is correct? So velocity is equal to the square root of the tension divided by the linear mass density. It's also equal to frequency times the wavelength. So I'm increasing the tension. So this is going up. The wave speed increases and the frequency increases. The wavelength is based on your string length, right? And your string length is not able to change. So, I mean, by changing the tightness, you kind of change the linear mass density a little bit. But, I mean, right, we're saying that it's this distance. The wavelength is fixed based on the distance. Now, if you touch different frets, like on a guitar, you're changing the different length of it. A wave of frequency 5 hertz travels along a string with a speed of 20 meters per second. The phase difference between oscillations of the string separated by 1 meter along the wave is. So what's our wavelength? So our wavelength would be our speed over our frequency. So I don't know why I wrote 30 when it's 20. 20 divided by 5 hertz tells me that it's 4 meters. So this whole thing is 4 meters. So that means that this is 1 meter, this is 2 meters, this is 3 meters, and that's 4 meters. So this would be a pi over 2 difference, right? Because the whole thing would be 2 pi. Two strings, one thick and another thin, are connected to form one long string. A wave travels along the string and moves the point where the two strings are connected. Which of the following does not change at that point? Well, the speed's going to change, right? Because the linear mass density changed. The amplitude's going to change. So it is down to frequency and wavelength. And frequency would be the thing that stays constant, because that's from however you generate the frequency, right? In a standing wave, the nodes are positions of maximum amplitude. That's not true. All points on the wave vibrate with the same amplitude. We know that's not true from the microwave demonstration. The distance between successive nodes is 1 wavelength. No, because that would be a half a wavelength. All points between a pair of nodes vibrate in phase. Yes, it's a standing wave. Two sinusoidal waves travel in the same medium, but one with twice the wavelength of the other. Which of the following statements is true? The wave with the longer wavelength has a higher wavelength would mean a lower frequency. All right, so when these overlap somewhere in the middle, well, let me put this on the bottom so it's easier to see. I need to add them. Why don't I do this on the next one? Because I have to be in a meeting in like 2 minutes.